Shell structures are timeless, resilient, and efficient, and have long fascinated architects. But the question remained, could these classic forms be adapted for evolving world of additive manufacturing?
We explored various typologies of in-plane compression-based structures, each presenting different challenges for 3D printing and the assembly. Concrete, with its inherent strength in compression, was chosen as the material for this exploration. Guided by its properties, we chose four different types of shells, each optimized to resist compressive forces.
From this exploration, we selected a system that balanced structural stability, ease of printing, and practicality in assembly. The chosen form is a shell spanning 2.7 meters with a thickness of 1.7 meters and a height of 4 meters, a catenary vault structure with a small opening at its apex. Moving from design to production meant translating digital precision into real-world fabrication. Every decision in the virtual model directly shaped how the structure would be printed.
In standard concrete 3D printing, layers are deposited horizontally. However, when printing curved surfaces like shell, these approach creates overlap between the layers. To address this, we adopted a non-planar printing technique using a 6-axis robotic arm that follows the natural curves of the form, much like tracing along the grain of wood to produce stronger and smoother surfaces.
To optimize for fabrication, the shell was discretized into 6 parts, each split strategically for printability, handling, and transportation. The segmentation wasn't random. We used algorithms to divide the structure according to the curvature and print planes. So the final goal was pretty simple. We had to reduce the supports, ease of handling, and we had to ensure that each piece fits accurately with each other. Inside every module, custom voids serve a dual purpose. They reduce weight and create channels for utilities. The precision offsets ensured these patterns never compromise the outer surface. Finally, the G-code was generated, translating the design into machine instructions. Over 200,000 coordinates were produced, each carefully optimized to balance material flow, robotic motion, and structural integrity. We observed the machine in operation, its movements orchestrated with precision and rhythm. Each motion carefully deposits a layer of concrete, methodically building the foundation. Every action is deliberate and calculated, gradually constructing the structure layer by layer. The process of printing has provided valuable insights. We developed strategies for managing overhangs, optimizing the use of rafts for stability, and ensuring structural support both during and after the printing process.
The guidance provided to us by the team at Tvasta was crucial in understanding 3D printing at this scale, as we've been doing it for the first time. During this process, we had key observations that made us understand this process better, which are visible lines are produced when the infill pattern is printed before the external surface. Given the heavy nature of concrete and the inclination of our elements, we had to support them externally using sandbags. Manual intervention was needed at the start and the end of the finish to ensure a clean and proper finish. And we were able to print overhangs up to an inclination of 83 degrees without supports, beyond which we had to support the prints using cardboard or acrylic sheets.